In this lesson, we're going to continue our study of relationships between categorical variables, and we're going to talk a lot about words and things that you hear in the media if you read about studies and things. So the first thing is we're going to talk about risk, relative risk, and then misleading statistics about this. So risk is calculated by finding the number of people in some category, or number of things that could, because not all studies talk about people, number of things in some category, and then dividing by the total number you have in your group. So, for example, let's suppose you tested a drug on a group of people and there was a side effect of getting a headache. The risk of getting a headache would be the number of people or things who got a headache divided by the total number of people you had in your group. And the relative risk compares one risk to another, and this is equal to the risk in category 1 divided by the risk in category number 2. Now, let's just talk about a couple things related to relative risk. If two risks are the same, the relative risk is going to be 1. That's because the risk in category 1 divided by risk in category 2 are the same number, so that's going to be 1. When the category in the numerator has the higher risk, the relative risk is greater than 1. And when the category in the numerator has the lower risk, the relative risk is less than 1. Now, the risk in the denominator of the ratio is often, although not always, something called a baseline risk, and that's the risk for a category in which no additional treatment or behavior is present. And the percent increase or decrease in risk, this you find using the formula relative risk minus 1 times 100%. So the National Health Interview Survey is an annual national health survey of people living in about 35,000 randomly selected households in the U.S. On the basis of the data collected in the 2006 survey, the CDC estimated that 15.7% of boys and 11.2% of girls under the age of 18 had at some time been diagnosed with asthma. So find the relative risk of ever having asthma for boys compared to girls. So 15.7 as a decimal, that is the relative risk for asthma if you're a boy. 11.2% as a decimal will be the relative risk for girls. And actually, if you put 15.7 over 11.2, it's going to give you the same answer as putting 0.157 over 0.112. So the relative risk is equal to 0.157 over 0.112. And the whole boys compared to girls means boys go in the numerator. So that is about equal to 1.4. So what you could say there is that boys get asthma at a rate 1.4 times higher than girls. What is the percent increase? Well, that's relative risk minus 1 times 100%. So 1.4 minus 1 times 100% is 40%. So there's a 40% increase in risk. Another thing that comes up an awful lot are odds, and less frequently the odds ratio. But generally speaking, the odds of an event compare the chance of that event happening to the chance that it does not. Odds are typically expressed using a phrase with the structure A to B. The ratio is implied but not actually computed. So this happens a lot with betting. The odds of you winning are 5 to 1. mean you would win 5 times for every 1 time you would lose, stuff like that. So suppose there's a 60% chance it will rain tomorrow, making it the chance that it will not rain 40%. What is this ratio expressed as a comparison of the chance that it will rain to the chance that it does not? So that will be, chance that it will rain is 60% to 40%. And this is like a ratio, so these can be reduced the same way that ratios can be reduced. Dividing both by 10 would give us 6 to 4, but even better, now we can divide both sides by 2 and we'll have 3 to 2. An odds ratio compares the odds of an event for 2 different categories. It's calculated as the odds in category 1 divided by the odds in category 2. And much like the relative risk, when the odds are the same, the odds ratio is going to be 1. When the odds of an event are higher in the category in the numerator, the odds ratio is greater than 1. And when the odds of an event are lower in the category in the numerator, the odds ratio is less than 1. Okay, for each of the following measures, give the value that implies no difference between 2 groups being compared. So if you compute relative risk, the 2 groups are the same if the relative risk is 1. What this means is that the risk is the same in each category. Okay, odds ratio, same thing, also 1 for the same reason. All right, percent increase in risk. Well, there will be no change if the percent increase in risk does not change, so that will be a 0% increase in risk. So no increase. Now suppose a study was done to compare the side effects for 2 different drugs that were used to treat some medical condition. 100 people are given each drug, and results are shown in this table below. For the headache side effect, we're going to compute the following. So they tested for headache and nausea. We are just going to look at the headache portion of this. So what is the risk of experiencing a headache for each drug? So risk for drug 1. So how many people had a headache while on drug 1? Well, that was 10. Out of how many people total took drug 1? Well, that was 100. So 0.1 or 10%. And the risk for drug 2, in drug 2, only 5 people got a headache, also out of 100 total people taking drug 2. So that's just 5% or 0.05. Notice that we had to actually know that the rows totaled to 100. So, and that wasn't given here, but it shouldn't be very hard to figure that out. Now the relative risk of a headache for drug 1 compared to drug 2. So remember that the relative risk is the risk for category 1. So in this case, that's drug 1. So risk drug 1 divided by the risk for drug 2. So that's 10% over 5%, which is 2. So you're twice as likely to get a headache with drug 1. All of a sudden, I don't want to take drug 1. All right, let's find the percent increase in risk of headache for drug 1 compared to drug 2. So to find this, we take the relative risk minus 1 times 100%, which is 2 minus 1 times 100%, which ends up giving us a 100% increase. What this really means is you have the risk for drug 2 and then plus another 100% of that risk for drug 2. And then the odds ratio, this definitely comes up a lot less frequently, but when you're comparing the odds of a headache for drug 1 to compared to drug 2, the odds ratio for drug 1 is 10 out of 90. You actually take what would have been the odds and make them into a ratio versus 5 out of 95. And that's 2.11. And that one doesn't come up nearly as frequently, so it's not the most important one. Now suppose I told you that you have a relative risk of 1.53. What is the corresponding percent increase in risk? So to find this, we just use that relative risk minus 1 times 100%. So that's 1.53 minus 1 times 100%, which is a 53% increase. And suppose on the other hand, I told you what the percent increase was, could you find the relative risk? So we have relative risk minus 1 times 100% is equal to percent increase, which is 140 in this case. Okay, well, let's just take that relative risk and make it into a variable. Let's call it x. X minus 1 times 100 is equal to 140. Then you have to go back to algebra 1 and solve. So 100x minus 100 equals 140. 100x is equal to 240, and x is equal to 240 divided by 100, which is 2.4. So if your percent increase was 140%, the relative risk was 2.4. All right, now sometimes funny things can happen when looking at row and column percentages for categorical data, and one of them is so paradoxical that it has a name. It's called Simpson's paradox. So remember that an observational study is a study where researchers only measure and observe all variables, no treatments assigned. And a confounding variable is a variable that may explain or mask a relationship. And whenever you look at the relationship between variables, you should ask yourself, is there something that might be causing this relationship to be displayed? That would be a confounding variable, and when that variable is accounted for, it might completely change what's happening. So a pretty good example of that will make all of you coffee drinkers happy. So for a long time, it was thought that coffee drinkers had higher rates of cancer. And coffee drinkers around the world were sad because they probably they thought if they're listening to this evidence, they should give up their coffee drinking because, well, getting cancer is not very much fun, obviously. But here's something that happened. When researchers looked at the data again, and when they controlled for smoking, they found that drinking more coffee was associated with lower rates of cancer. And you say, holy moly, what am I to do? So the answer is go drink that Java. So, well, maybe I'm not a medical doctor, I shouldn't give advice in this video, but the point is that smoking was a confounding variable that changed or masked the actual relationship that was going on, and the relationship that was going on is that drink more coffee was associated with lower rates of cancer. It's probably the smoking that was leading to the higher cancer rates that were being observed. So in a 1997 Marist College Institute for Public Opinion survey of about 1,000 randomly selected Americans, 31% of the men and 12% of the women surveyed said that they have dozed off while driving. And you look at these percentages and you say, holy moly, like the men's percentage is way, way, way higher than the women's. And the thing you could think about, what would be a third variable that might at least partially explain the observed relationship between the sex of the driver and reportedly dozing off while driving? So one thing that I can think about is more men may drive as part of their job. And in that case, they spend more hours on the road. Another possibility is that men may do more night driving. And so there probably are other examples as well, but the point is there might be these other variables that are leading to that large discrepancy that you see. Now, the funny thing that happens is something called Simpson's paradox. And what this is that the direction of a relationship or difference is reversed within subgroups when compared to the direction within the whole group. Like that smoking thing, for example, when you separate out the smokers and non-smokers in one group, the smoker group, the incidence of cancer is going to go up versus the non-smoking group where it's going to go down compared to the whole group when it goes up. So what this says is that when the direction of a relationship or difference is reversed within subgroups when compared to the direction within the whole group. So the direction of a relationship or difference is reversed within subgroups when compared to direction within the whole group. So let's look at an example where Simpson's paradox comes into play. So the data for this example are hypothetical, but they're similar to the data from several actual studies. So this study is trying to look at the rate of high blood pressure in groups of people who use oral contraceptives and groups of people who don't. And we have 22,400 women who are categorized according to whether or not they use oral contraceptives and whether or not they have high blood pressure. So here's the data we have in this table. So let's compute the percent of people with high blood pressure in the using oral contraceptives category. Well, that's 64 out of 800, or exactly 8%. So 8% of the people who use oral contraceptives have high blood pressure, and of those who don't, 136 out of 1,600 is 8.5%. So it appears that not using oral contraceptives is associated with higher blood pressure, or using oral contraceptives is associated with lower blood pressure. possible confounding variable is age. And a way to control for age is to create separate contingency tables for women in different age groups. So what we did here is separated out the women between the ages of 18 to 34 and 35 to 49. So in the using oral contraceptives group, in the younger age group, 36 out of 600, or just 6%, have high blood pressure. And 16 out of 400, or 4%, have high blood pressure in the don't use group. And in the other age group, 28 out of 200, that's 14%, and 120 out of 1200, that's 10%. And the thing that's funny here is that you notice that the using oral contraceptives group in both categories, both this category and this category, the percent with high blood pressure is higher than this category, which is different than it was for the original group. So the thing to note, when age groups are separated, the percent with high blood pressure is greater in the uses oral contraceptives group and this is a reversal of the relationship in the whole group, which was a reversal in the relationship in the whole group. And that's the paradox. Now, another example of Simpson's paradox that's pretty well known examined admission rate for men and women who had applied to a graduate program at UC Berkley. So this data, the actual data is confidential, but this example uses similar hypothetical numbers. So here are the figures for acceptance. You have program A and program B, and we have how many people are admitted and how many people are denied. So the first thing we're going to do is we're going to combine the data for the two programs into a single table, and what percentage of the men who applied were admitted, what percent of the women who applied were admitted, and which sex was more successful. So first, making this into a single table. So we have men, women, admit, deny. And we'll have new totals as well. So the men who were admitted, well, there were 400 admitted and 50 admitted to program B, so that's 450. Denied, 250 plus 300 is 550. And of course there the total is a nice even 1,000. And for the women, there were 175 admitted, and it looks like 325 denied, for a total of 500. And then the column totals, which we're not going to need, but let's just find them anyway. The total number of men and women admitted was 625. And for denied was 825. Okay. So now using this table, what percentage of all women who applied were admitted? So the percent of women admitted is equal to 175 out of 500, which comes out to be exactly 35%. And then the percent of men admitted, well, that's 450 out of 1,000, or 45%. So based on this, it appears that men are more likely to be admitted. Okay, except when you look at this in the individual programs and you break the data into these two groups, it's going to be reversed. So what percentage of the men who applied to Program A did Program A admit? So men, Program A, we have 400 out of 650 total, which comes out to be 61.5%. Okay, so for the women, Program A, we have 50 admitted out of a total of 75 women who applied. Well, that's about 2/3, or 66.7%. Okay, Program B. So men, Program B. 50 were admitted out of the 350 total. So that's just 14.3%. And the women, Program B, admitted, there were 125 admitted out of 425 applicants, which is 29.4%. Okay, so notice that in this case, when we look at subgroups, the women were more successful in both programs. Okay, so which sex was more successful in each program? Women were more successful in both programs. So explain how this problem is an example of Simpson's paradox and provide a potential explanation for the observed figures by guessing what type of programs A and B might have been. So why it's Simpson's paradox is because in the overall group, one category, men, was more successful, but when broken into two groups, the women were more successful in both of those. So in the overall group, or in the whole group, and that's when the data was combined, the men were more successful, or admitted at a higher rate. But when broken down by programs, women were more likely to be admitted. And that's what Simpson's paradox is. And for Simpson's paradox to happen, I mean, there's nothing that in this class we're going to talk about that will tell you how you know it's going to happen, but I think it has a lot to do with the fact that in, like, say, Program A, this subgroup is such a much larger size than this one. So that probably has something to do with it. So thinking about that, program A is a program that probably is a male-dominated field. So program A is probably a male-dominated field. So it might be something like math, physics, possibly engineering. And program B appears to be something, I don't think it's obviously women dominated because 350 applicants versus 425 isn't so big. So program B is a bit more a more evenly liked field. And that could be something like medical school, for example, or psychology. There's no really right or wrong answer, but except for the fact that program A is almost definitely male-dominated. You can also probably see that there are probably lawyers arguing over this, that somebody probably claimed that there was sexism going on because in the overall big group it looked like men got in at a higher rate. But then the other lawyer argued that no, it's this paradox going on, and when you look at the programs individually, you see that women actually are more successful. So one more way that math can be used to argue stuff in real life.